Hi everyone, let's talk about the pancreas and its physiology. Technically, we are talking about the endocrinology of the pancreas today, and that is important to say because the pancreas can be both an endocrine and an exocrine organ. Looking at its structure at the gross anatomical level, this pancreas here is closely associated with the duodenum, and it's also connected through a duct system to the liver. And with regards to its exocrine function, we have the creation of different digestive types of enzymes referred to as the pancreatic juices that are created and they flow through the duct of the pancreas called the pancreatic duct and meet up with the common bile duct from the liver. And those products are squirted into the duodenal portion of the small intestine to aid in digestion. On the outside, when we're looking at it from just the organ perspective, we have two main pieces. We have the tail of the pancreas, and we also have the head portion of the pancreas, which is closest to the duodenum. And with regards to the microcellular portion, we have the cells associated with the functionality. We have those who are more exocrine in nature, acinar type cells or acini, which secrete different enzymes to go through the pancreatic duct. And then we have the islets of the, I just made a little dot. Oh no! Pancreatic islet, which is made up, I don't know how to reverse this. That's the face I'm giving it, that contain both the cells that make glucagon and those that make insulin. Perfect. It's back. It's great. Those cells are referred to as alpha cells and beta cells. So let's take a look at some other things about the pancreas. Again, we've got its head and then the tail portion. We can also see here, again, its relationship with the bile duct from the liver and the duodenum. It can be endocrine or exocrine in nature. We already mentioned that that duct is used for digestive juices, and the endocrine functionality of the pancreas is associated with these two big hormones, insulin and glucagon. Taking a closer look at those islets, the islets of Langerhans. This is a little functional unit of the pancreas where these cells are just organized. We can see that the acinar cells, they're arranged in a circle-like fashion so that they can secrete their products into the ducts at the center, whereas endocrine cells, they will secrete products directly into the bloodstream. We have beta cells associated with insulin, we have alpha cells associated with glucagon, and we also have delta cells, which make a specialized product that you may have learned of in other places called somatostatin. This is just a little schematic showing you an organization of these cells. About 25% of the cells in the islet of Langerhans are alpha cells that produce glucagon. 60% are beta cells that make insulin. The delta cells are what make somatostatin, and somatostatin is what helps turn off or stop a lot of digestive processes. With regards to insulin and glucagon, it turns off their activity. It actually acts as an antagonist for them. Then we have cells that are sometimes called PP or F cells, which make something called pancreatic polypeptide, which has a relatively obscure function. That doesn't mean we can't pretend they're not there. And endocrinology in the pancreas is all going to focus around the activity of insulin and glucagon. They do work in an opposing fashion whereby one is going to block the portion or the functionality of the other. Here's a little schematic showing you the way that these work in concert. And you might know that when people have diabetes and they need to take insulin, it has to do with having high blood sugar. And that gives you a nice window into what insulin does. When insulin is around, it helps move glucose or sugar into places that will utilize that glucose so that it's no longer out in the bloodstream. So here we see high blood glucose that in and of itself triggers cells in the pancreas to make insulin. That insulin helps move glucose into cells that use it, like adipose cells or muscle cells. And that means that it now vacates the bloodstream, so that will normalize blood sugar. The pancreas should stop making insulin when we get back to homeostatic levels of glucose. Conversely, when blood sugar is low, that signals to cells in the pancreas that we need to get some sugar out into the blood, so we need to get it from stores. The product that drives that is glucagon. Glucagon is made by those alpha cells, and whenever glucagon is around, it helps break down that glucose that's been stored in those tissues so that it's now in the bloodstream. It can travel around the body and get to tissues that need it. So it's simple feedback loop here. It's not an axis feedback loop. It's called a physiologic feedback loop, where things are released in response to only a physiologic level of something. And in this case, it's glucose. So when there's high blood glucose, insulin is released, and it is released until we get down to this homeostatic set point of normal glucose. Then its production is going to shut off. Whereas low blood glucose is going to trigger glucagon release, which is released until our blood glucose gets back to homeostasis, and then that is turned off. So the only thing that is controlling glucagon and insulin release is levels of glucose in the bloodstream. There are only two types of cells in the body that are permeable to glucose at their resting potential. That means there's only two types of cells where glucose can enter normally into the cell. Those two types of cells are brain cells, so neurons can always take in glucose because your brain loves to run on glucose. The other type of cell that can let in glucose at resting is the beta cell, and beta cells make insulin. So the way that glucose gets into beta cells, if we look right here, when glucose starts to rise in the bloodstream, it enters cells through a transporter called the GLUT2 transporter. Because how else would beta cells know how to make insulin? Well, they need to sample the glucose in the bloodstream. And when glucose gets over a certain level, it can now traverse into beta cells. So it enters through these GLUT2 receptors, it goes through a phosphorylating pathway, and it eventually activates these potassium channels, which will close and depolarize or activate the cell, open up some calcium-gated channels. Whenever calcium enters a cell, it's going to drive docking and fusion of the vesicles inside of it to the membrane so that those vesicles can fuse with the membrane and empty their contents out of the cell. So glucose comes into beta cells through the GLUT2 transporter, opens up some channels, and then we get the exocytosis of insulin. So we need the GLUT2 in order to get insulin release. This is a graph showing you a pretty simple schematic of insulin levels relative to plasma glucose. So as glucose levels in the plasma go up, we see that insulin secretion also goes up. So insulin levels will continue to go up as long as glucose levels go up. We can only get glucose moving into cells if we have insulin there to let it in. The way that this looks throughout a meal, for example, is this graph right here, where when we are looking at the red line, we're looking at levels of insulin in the plasma. In blue, we have what the glucose levels in the plasma would be like. So this would be, for example, this is a controlled experiment where they're infusing glucose into a patient, but this would be the same thing you would see if you had a nice meal. So initially when you start eating and things are broken down into its component products like glucose and other starches and sugars, we see that glucose levels in the blood go up, and then we have this nice spike in insulin. And it's almost immediate, and then it starts to level out a little bit, and then it will rise slowly over the next about an hour. So within 10 minutes of eating, you have this really large spike in insulin production. It's called the early phase. And then we have the late phase of insulin that's going to slowly rise over the next time. In order for glucose to get into cells, we first need insulin to open up receptors in that cell. Again, there's only two types of cells that glucose can get in normally at their resting potential, and they are in your brain and they are beta cells. However, all the cells in your body run on glucose, right? We need to get it in there somehow. Well, insulin is what does it. It's like it has a special knock, and when you hear insulin knocking on the door, even if it has glucose with it, you will open up the door to let in the glucose. And that's insulin's job. It is there to move glucose. We do not let, there we go. We don't let glucose in without insulin first getting there. It's an anabolic hormone, so it helps to maintain upper glucose limits, free fatty acid limits. With seconds of binding to receptors, body cells move in the glucose. Without insulin, glucose is not likely to move into a cell. Whenever insulin is around, uptake of glucose goes up, utilization of glucose by muscle and adipose tissue goes up, and we also start to store it as glycogen in the liver and muscles. So that's insulin's job. Insulin and growth hormone also work really well together. What happened? Whenever we have those two things working at the same time or released at the same time, they act in what we call a synergistic way, which means they work better together than either one do on their own. So here we're looking at a study where we're looking at weight of a subject, and then we're looking at days. In this study, there was a removal of the pancreas and of the pituitary. We gave exogenous growth hormone and weight goes up a little bit. We give exogenous insulin and weight goes up a little bit. We give them both together and we see this huge spike in growth. So insulin not only is going to move glucose, it also enhances the activity of growth hormone so that tissues, especially long bones and muscle, grow more effectively. Again, the opposite of insulin is glucagon. So whereas insulin lets glucose into cells to lower blood sugar levels, glucagon is what raises glucose levels. So think about it as during the night when you're not eating and you're sleeping, your brain still needs glucose to work and run your body. So we have glucagon that's released. And whenever glucagon is released, we increase breakdown of glycogen, glycogenolysis. We also increase gluconeogenesis, which means the creation of new glucose. So we can liberate stored glucose from its storage what's the word I'm looking for? From its storage, identity as glucagon. So whenever glucagon is released from alpha cells, we are going to affect all of these pathways that increase glucose liberation from storage and allow it to be used, especially during fasting states. A graph that was similar to the one we looked at earlier with insulin. Here is plasma glucagon on the Y, so glucagon levels. As glucagon goes down, we see that blood glucose also goes down. So when glucagon levels are high, blood glucose is high. Its job is to raise blood glucose. When blood glucagon is low, blood glucose is low because it's not being secreted. So therefore, we don't have a ton of glucose in the blood. And that's it. So that's with regards to the pancreas. We've got those two products. They're working in opposition. Insulin lowers blood sugar and glucagon raises blood sugar.